guys, I hope you're doing all well. So I'll just do a small tutorial, 2 problems for you to have a fun and try to go through it. So we have a transmission line of 100 ohms, as you can see, connected to a load of 50 ohms resistor in series with a 10 picofarad, as you can see here. So this is the input here, this is the Z transmission line, Z0, of course, characteristic impedance, and this is the series. Now, gathering all the information, you can see here we have the load impedance. We say is in series. So to find the load impedance first, we need to find R plus 1 over G omega C, which you have this. So this to find the load impedance. Therefore, the load impedance here is 50. You just apply the numerical numbers and you can find that the load impedance is 50 minus J 159. Now to find the reflection coefficient as is asked, we know the formula from 1.28. So you just apply the raw formula and we have this. Okay, so therefore we need to find the conjugate to find the reflection coefficient in the polar form. So here we have this. After everything, we're gonna see that the reflection coefficient is this minus this. So the magnitude, as you can know, you need to find the magnitude, of course, of this, which is this one. And here we have the reflection coefficient in the phasor form. So here it is in the polar form. So definitely, if I ask you to find this one in terms of exponential, you need to convert this one into radian to find it in exponential. So finding the impedance at the input when the length is 0.125 lambda means L is 0.25 lambda. Remember, we need to apply this equation 1.29. Of course, it is a lossless transmission line, mean propagation constant is J beta. So we apply the formula, which is this 1.29 according to the note. We have this. We have beta, which is 2 power lambda, and beta L. So this one, beta L, is 2 pi over lambda times this. This is given, so we cancel each out. We have 0.25 lambda. So now to find the remaining Z in, so we have this. We apply, we find this, and we come out with this one. So this is the input impedance 1.07. This one. Now this in polar form and this in phasor form. Don't forget again, I say you can convert to into radian. To convert this one into radian, we have minus 87 times 4. We have to divide over 180 degrees times pi to find it into radian. If you want to write it in terms of exponential, J theta L, and this one is in radian. Okay, theta L. So this is the first problem. The second problem now is this one. We have a lossless transmission line with characteristic impedance 50 ohms connected to a source 60 ohm with a frequency of 100 megahertz, and the source impedance is 50 ohms. So when I gather the information, I see VG 60 ohm, Z is this. The transmission line has a length of 1.5 and the characteristic impedance is 50 ohms. So this is the information of the load. So we assume the speed of the wave along the line is equal to the speed of light. That means UP equals C. That one it means. So now this is my figure here, as you can see. I'll draw it for you. This is the source here, this is the load, and this is the information on the transmission line. To find the reflection coefficient now, we have to apply the same at the load. So we apply the raw formula. The numerical application is this one, as you can see. After having everything, we have this one, we have this one, again this one in polar form, and this one in phasor form. So again this one, I can write it, it's 0.45 exponential J theta L, and theta L here is 1.107. You just need to multiply this one and divide by 180 degrees to find this one. Okay, so to find the input impedance now, again the same. we need to look at the input. At the input, we need to apply the same equation 129. We have this. We need to find beta d. We have beta 2 pi over lambda. First, we find lambda. Lambda is 3. Then beta will be 2 pi over 3. Then we just apply it straightforward here. And you can see Z in is 50 plus 50 ohms. Of course, if you want, you can write it into polar phasor form because it's polar form. Now to find the current at the input, of course, it's VG. As you can see here, we have here the current here I, we have the source, we have Z, we have Z coming. So therefore the current at the input is the voltage over the resistors, which is Zg plus Z in at the input. This is what we have here. So this is the current here, as you can find. So after finding the current at the input, we are asking to find the power delivered to the load. Okay, so the power delivered to the load, this is the formula, if you might recall, which is the magnitude of the current squared times the real part of the input impedance. So you have to find this is the current here we found. So this is the current. You need to find the magnitude of the current, which is the magnitude we give us 0.536, as you can see here. Square times this one, then we have the power delivered here. And nevertheless, remember the input power is equal to the output power. That's why we are using the input current, because it's a lossless transmission line. So the equal power transmitted is at the input is the one we have at the output. So these two programs we stop here for students for FBC. Don't forget to subscribe to my channel, and we see you very soon in class. Thank you.